Hold on, we're just gonna go live. Let's continue this conversation once we're live. All right, we're live. And then, oh, there you are. Okay, good. Yeah, my dabbling in machine learning so far is very much that it's like you can teach a computer to recognize a thing, and you can teach a computer to categorize a thing with your machine learning, and that's about it. I mean, you're not making your plastic pal that's fun to be with. You are making just does some very, very narrow jobs very well, very quickly, better than humans.
Yeah, and it's also very limited to what you can teach it. So if you've got a training data sample that's like perfect, you can teach it to work perfectly there,
Yeah.
but take that to the real world and it won't work at all.
Yeah, yeah. I mean, like interesting, like doing transformations. Like you have it image recognized, and then you turn it 90 degrees, and then suddenly it's just like I don't know what I'm looking at anymore.
Yeah,
Yeah, it's the
exactly.
same thing. It's just yeah, but they just can't recognize it. But then you see these really interesting like advances in things like GPT-3 and stuff, and you're like, there's something there, or like the
Yeah,
doodles, the OpenAI
yeah. I
Dolly.
think some of the models nowadays are like moving towards learning to learn. So you're instead of teaching a algorithm to learn a specific task, it's trying to teach it as many different tasks as possible so it can learn to do new tasks that it's never like encountered before.
Yeah, yeah.
It's pretty cool.
Oh, you know what? I should introduce you. This is always the way it goes. Is that we're chatting before I press the live button, and we just keep talking, and then at some point it occurs to me that this has turned from me hanging out with somebody to an actual live stream that people are going to be able to watch us. So who are you? What do you do?
Okay, I'm Dr. Maggie Lieu. I'm a research fellow at the University of Nottingham, that's in the UK. And I research galaxy clusters, which are the largest gravitationally bound objects in the universe, is everyone's liner for what these objects are. And they're the best laboratories that we have to study dark matter because they are huge potential wells, huge like sacks of dark matter. And I've been developing machine learning algorithms to try and work with galaxy clusters in preparation for a new space telescope launching in 2022 called the Euclid mission. And that's one of the European Space Agency's upcoming missions.
So this idea of mapping dark matter, and I'm sure we've all seen these incredible three-dimensional maps of the dark matter surroundings. What is the technique currently that astronomers use to map out this invisible thing with such I don't know, with such amazing sort of specificity?
Yeah, exactly. So, unlike ordinary matter, dark matter doesn't interact with anything. So, it doesn't emit any light that we can see. It's essentially invisible. But it does have gravity. So, it can have a gravitational influence on surrounding objects and also light passing within its vicinity because it has a huge gravitational potential well that light will follow the curvature that this gravity creates, essentially. And this bends the light of galaxies behind dark matter. So if you're looking at the sky and there's a big clump of dark matter in your field of view, galaxies behind it, that light doesn't travel in a straight line anymore. It curves around the potential of the dark matter. And so that causes the galaxies on the sky to appear warped or bent. And this is called gravitational lensing. And that's how we measure where the dark matter is on the sky.
And the joke that I always make is, we don't know what dark matter is, but we can use it as a telescope. So, so it's sort of like a almost absolutely necessary tool for being able to both sort of perceive the universe as it really is, but in some cases be able to see farther than we could normally with our existing telescopes. I mean,
Yeah, in particular for strong gravitational lensing. So that is where you're in the maximum like vicinity of this lensing power. And using like areas like that, you can see much further away galaxies than we have been before. It's like a magnifying glass, essentially.
Yeah.
It works exactly the same way.
But it's interesting to me. I imagine it like you're looking into a pond or the ocean, and you're seeing these ripples in the water that are changing the distorting the ground, and in your case, you're able to then recreate the ripples in space, just from how they slightly distort various stars and objects. It's kind of a stunning thing. This takes a lot of computers, right?
So specifically for me, I use an effect called weak gravitational lensing. And so I guess galaxies are already like elliptical, and they have all different types of shapes and orientations on the sky. And gravitational lensing for me, like the dark matter, changes the shapes of these galaxies by order 1%. So their shape, like the noise is much larger than like what we can measure of the change in the shape. So we have to average over thousands and thousands of galaxies, and you see like a tiny like change in the shape overall over this average. That's what we can use to say.
Okay, all right. So you know that the shape that a galaxy should be, and then you have a big picture of the sky. You measure the shape of one of these galaxies, and you can tell by how it's being distorted that there's a blob of dark matter in front of it, yes, or something.
Yes,
and
exactly.
And how precise is that? I mean, you say 1%. Like where does that tail off to the point that it just sort of falls into the noise of your image?
Well, the closer the galaxies are to the dark matter potential, and the larger the dark matter potential is, the more the shape changes. So you get a sense of the signal simply from the amount that it changes by. But the more galaxies that we have that we can average over, the better measurements that we can have, the more precise measurements that we can have on that dark matter signal, essentially.
Yeah.
So that's why Euclid is so important, because it's mapping billions of galaxies in space, whereas a lot of our telescopes are observing from the ground. And we're making these like percentile precision measurements, but looking through clouds and looking through distortions in the sky, like temperature fluctuations on the sky will affect our measurements of galaxies anyway. And the noise and all sorts of things. So
Euclid is essentially going to be taking these images of the night sky, or I guess from space, and it's always night sky in space, and doing those sort of really precise measurements. So just give me a sense of like how many pictures is it going to be taking, how much of the sky is it going to be observing, sort of at what pace?
So it's observing a third of the entire sky. And that doesn't sound like a lot, but it's looking very deep into the sky as well. It's a lot if you put it in the context that every night it's going to be downloading 100 gigabytes of data. So like, I don't even have 100 gigabytes of space on my computer to store this stuff.
Yeah.
And it's going to be doing this for 6 years.
Right. And that's the baseline. Often these missions last a lot longer than anyone's anticipating. So it will continue to peck away at the rest of the sky if it's able to stay up there longer, I'm assuming.
So Euclid is not looking into the plane of the galaxy because it's so dusty in there. There's not much that we can see through. It would just be
zone of avoidance. Yeah. And so you're looking like above and below the galaxy.
Yeah.
Right. Okay.
Yes.
And so when does it launch?
So it's launching in 2022. Fingers crossed. I think in September. But if it doesn't launch in then, it might have to change like rockets. At the moment, it's planned to be launched on a Soyuz rocket, but ESA are launching their Ariane 6 rockets next year. So if it doesn't make its 2022 launch, maybe it'll have to switch to that.
So, you were saying like a Soyuz, so it would be launching out of like Baikonur? Was that right?
I think it's still launching from French.
Oh, from Ghana, right? Okay, from the Kauru, right?
Yeah.
Launch facility. Yeah, the same place James Webb is going to be flying from. I'm sure it'll be fine.
Hopefully that's not delayed
No,
as well.
it'll be fine.
That's like constant.
Yeah, there's no way it's going to launch sooner than James Webb. It'll launch on time. Everything's going to launch on time from here on out forever. Okay, so you're going to get this third of the sky survey captured by Euclid. It's going to be taking these really precise images of the night sky, providing the best measurements you can possibly get of the shape, the distortion of these galaxies from what you would expect them to be. What does this tell you beyond you've got a better map of dark matter? What does this help you understand?
So dark matter is particularly important because we don't understand it. So Euclid, its name comes from Euclid the mathematician, and mostly because of his relation to geometry. And Euclid is looking at the dark universe, and the geometry of our universe is relating to the density of dark matter and dark energy, the thing that's making our universe expand acceleratingly. So besides these extremely precise measurements of shapes of galaxies, another main kind of goal for Euclid is something called baryonic acoustic oscillations. So this talks about in the very, very early universe, matter and photons and radiation, they were coupled together. And at some point they broke apart, right? They separated. And this, when exactly this happened, creates a very signature like peak in a thing that we call the baryonic acoustic peak. And it's seen in the separation of galaxies. So if you measure the separations of galaxies, you'll see that if you just plot a density of how far apart each galaxy is from each other, there'll be loads that are really close together and less that are further, opposite way. Loads that are further apart and then less close together. But then there's a certain distance that you have a peak in the separations of the galaxies. And this is specifically due to that separation time.
It's kind of, it's such a fascinating idea that conditions that were there shortly after the Big Bang lead to the large-scale structures of the universe that we see all around us as these sort of echoes of what came before. That if you run the clock back, like things that are thousands, millions of light years apart from each other were right next to each other back at the beginning of the universe. Can you give us a sense of, like, when you're talking about these oscillations, how big would these be back at the beginning of the universe, and then sort of how much of a factor do they scale up to today?
Well, these are particle scales, right? So these are back when like we're talking about matter scales, and now we're on galaxy scales. Obviously, back then, like galaxies hadn't formed then; it was just matter and radiation. So now we're fully formed galaxies and galaxy clusters. All these substructures are forming essentially due to dark matter pulling us together and dark energy pushing us apart, causing these giant voids that we see in the cosmic web, and these kind of filaments and substructure due to the gravity between all the matter. But
I guess I'm saying like when we see this, a concentration of, a galaxy cluster, some kind of galactic wall with a bunch of galaxies separated by a giant void, if you ran the clock backwards, you would get a time when these voids were smaller, that the galaxies were maybe not quite as concentrated, and you keep going back and you get to the cosmic microwave background radiation with different overdensities in the cosmic microwave background. If you keep going back, you get to the point where you're saying this is on the particle scale, that if the particles were like a little bit different,
exactly,
then literally the galactic cosmic voids between would be a different shape or a different scale or a different distance or any of that. Like as close as an atom? Like how close?
yeah. As close as an atom. And actually, that's something that I work on as well, cosmology. One of the things that I constrain with my galaxy cluster measurements is called sigma 8. So this is a measurement of the fluctuations in the very early universe on 8 kiloparsec scales. So how large were these fluctuations on that scale? But they were tiny scales, really.
But it's sort of fascinating to think that the universe, literally the expansion of the universe, has become a magnifying glass for the conditions at the early universe. And so, as you say, you get these very precise measurements of the galaxy's distribution, the amount of dark matter, whatever, and it allows you to run different particle physics theories at the beginning of the universe, because you've essentially things have just kept on going on and expanding.
The universe will just look completely different if the conditions at the early universe were a little bit different. Yeah,
and so then, based on what we know today, what does that tell you about how those conditions were like at the early universe, do you think?
Well, at the moment, we have this big dilemma, actually. Our cosmological measurements of galaxy clusters, which we observe today, particularly number counts of galaxy clusters, they don't agree with early measurements of the universe. So cosmological measurements we have from the cosmic microwave background, which we know was emitted at the very start of the universe. So you can use various different probes to probe these kind of initial conditions of the universe, but you'll get very different answers. And that's a huge tension we're still trying to solve at the moment. It's a big dilemma.
Right. Well, the cosmic microwave background, I mean, that only gets you to like 300 and something thousand years after the Big Bang. And so prior to that, there's no way to directly probe what the universe looked like. Maybe we're going to get a chance to see it through gravitational waves, maybe through the background neutrinos. But this sounds like this indirect expansion is like another way, beyond just math, beyond just you calculating what the early universe should be like. This gives you a way to go, if the universe looked like this, then you would see this. And if it looked like that, then you'd see that. And Euclid will tell us which one it's going to be. So, which of these, I think about it, when you get one of these observatories that's got this very precise job, it usually means there's two camps and they can't agree yet on which way things break. And so they need a more precise measurement to finally come to some kind of agreement. So what are the camps as it relates to the sort of scale of the early universe at this point?
So the camps still are that, like, you don't expect these cosmological parameters to have changed with our current theories. We expect the CMB measurements and our current probes of cosmology, like clusters and supernova, we expect them to all give us the same answer, but they don't. And so there must be a different theory that is able to explain why our measurements are different, because this is already within within the uncertainties that they're what, three or some are, I think, 5 sigma tensions, right?
Oh, so are you talking about like the two measurements for the Hubble constant, like from the early universe and from the more recent one? Okay.
Yes.
Yeah. The crisis in cosmology.
Yes.
And so will Euclid be able to help give an answer to that?
Yeah, so that's one of the cosmological parameters that Hubble is going to measure, one of many. So as well as dark matter, dark energy, the Hubble parameter is a really important one as well.
Yeah. So you're, in the, like, you spend more of your work in dark matter, dark energy. Which part of the dark universe do you tend to spend more time thinking about?
So I think about cosmological parameters, and with galaxy clusters, they're most powerful at constraining omega matter, which is the density of matter in our universe, and sigma 8, which is those fluctuations that I spoke to you about before, the oscillations in the early universe. So those are the most easily constrained with clusters of galaxies. But you can also use it to constrain the mass of neutrinos, the Hubble constant, and other cosmological parameters as well, because these are the largest objects in our universe. So of course they have constraining power on the universe as a whole. Yeah, I think most people are excited about the neutrino masses.
Yeah. And so as it comes down to the crisis in cosmology, just these different measurements for the Hubble constant from more recently, and what we see in the CMB, what explanation feels most satisfying to you currently, pre Euclid result? Where do you think it's going? Where do you place your bets?
Honestly, I think we need a new theory.
Yeah.
Like, general relativity works pretty well, but it doesn't coincide with like the smallest scales. It doesn't agree with particle scales, right? It only works on the largest scales, but maybe it doesn't work on the very large scales, like universe scale, and that would be able to correct things. I think if we can find a theory of everything to cover all of these scales from the tiniest to the largest. I mean, even when Newton came and discovered gravity, right, that was wiped out when we realized it didn't work on our planets and on satellites and things like that. So on the largest scale, like on the smallest scales, Newton's gravity works perfect. You could go to the Leaning Tower of Pisa and drop a feather and hammer, and they would land at the same time. And Newton's gravity predicted it perfectly. But on larger scales, on planetary scales, it just doesn't work. So we need those extra corrections that are given by general relativity to make things work. And maybe on the universe scales, we need something else.
So, but I mean, that's almost starting to sound like Mond a bit. Are you?
Yeah, I'm not a fan of Mond.
Right. Okay. Good. Yeah.
In Mond, it's like they always modify small bits, and they're like, okay, there's this new evidence that proves that our theory doesn't work. Let's add on an extra little bit to try and make it work. And it's more of a tweaking theory, whereas general relativity was just very elegant and it was beautiful. So I think when a theory comes along that is able to predict everything without doing all these little tweaks to make it work, that would be able to solve this tension, hopefully.
Yeah, I know what you mean. It sort of sounds like sort of Ptolemy's epicycles, that you're sort of, you're making the movements of the planets work by having things move in little circles around other little circles until finally the math holds. So, this idea of uniting the forces, of taking gravity on the one side and quantum mechanics on the other side, and right now they're oil and water, they just don't go together. But there are these really fascinating ideas both on both sides of it, to be able to try to experimentally see how things behave. I know that there's some people are taking like Bose-Einstein condensates and they're scaling them up as big as they can get them, because the whole thing acts like a one single entangled atom, that then you could maybe detect the gravity of it if you get it large enough. And it really sounds like you're sort of doing the same thing with Euclid. You're taking what was the particle domain, the quantum realm at the beginning of the universe, and you're scaling it up to the universe size, to the gravity scale, and watching as it smoothly transitions from particle scale or from quantum mechanics scale to gravity scale. Am I getting that wrong? Is it, because that's what it sort of sounds like you're doing?
No, you're getting it right, but like, so in a lot of our simulations that we use to base our observations on and to kind of compare to, these simulations start off with particles and they just evolve them over time with the standard like gravity and pressure inputs, all the physics put in, and they just watch these particles evolve over time to form our galaxies and our galaxy clusters, our universe as a whole. And that's what we base a lot of our theoretical models on, especially like me, all the models I have of galaxy clusters, we take simulations and theory-based models to compare to, and that's how we get our cosmological parameters out. The thing with simulations, though, is that you can't model every atom like in our real universe. We don't model every single particle because we just don't have the computational power to deal with that. You'll take a low resolution of it. You'll maybe like group lots of real particles together and you'll have a lower resolution simulation, or you'll have a smaller box simulation. So you don't model the entire universe as a whole, but maybe some small volume of it to, say, specifically look at a particular galaxy or a particular black hole. So depending on what you're looking at, you'll have different resolutions of simulations and different volumes.
I always say that astronomy is becoming more and more like computer science. And I often suggest to people, if they want to get a career if they want to be astronomers, also take some computer science. And that way, if the whole astronomy thing doesn't work out, you can always get a job at Google or Facebook or whatever and make millions of dollars as a backup plan. How much of your life now is about computers, and how much of it is about astronomy? Are you more computers than astronomy?
So I would say, like, since starting my PhD, all I do is code, and I don't own a telescope, so I don't know how you could call me an astronomer.
Could you do you know your constellations?
I do. Okay. I do know quite a few constellations, which is better than most astronomers.
Yeah, but, I know. I'm like, okay, find me Hercules, and they're like, I got nothing. It's like, it's right there. Yeah.
Yeah, it's really difficult. Like a lot of the observatories nowadays, they're all automated. There's no need to send someone to the opposite side of the world, to Chile or to somewhere else, to observe for a handful of nights and then come back again. It can all be done remotely.
And one of the things that I'm also a big fan of is this shift from sort of you asking for a specific observation, like you book some time on the Very Large Telescope and you're able to observe this tiny star system or galaxy or whatever, and now these giant surveys, things like Gaia, things like the Vera Rubin Observatory, Sloan Digital Sky Survey. How does that change your life as an astronomer / computer programmer?
Well, I think it's great for like people like me who are familiar with working with big data, because it's just the amount of data coming in. It's going to be so hard for a single person to process. And we're seeing more and more astronomers build larger and larger collaborations to deal with this. A lot of science is also like kind of interdisciplinary. So I don't know, so for example, the gravitational wave detections, they're relying on a lot of the other communities like gamma ray bursts and stuff like that to help them follow up for sources and other things. So you can get a lot of different science even on like a single topic that you're looking at. So for example, when I started at ESA working on Euclid, I went there primarily to work on galaxy clusters and weak gravitational lensing. But when I was in the meetings, someone said, oh, we've got all this problem with asteroids. They're like polluting all of our data. And, asteroids, they leave streaks on the images. And sometimes if they're moving slow enough, they can look like galaxies that are sheared by gravitational lensing, right? So that their shapes are distorted.
Or some kind of tidal tail or something.
Yeah,
Right.
exactly. So if you included an asteroid in your weak gravitational lensing data, that would mess you up completely because the signals are already only 1% like strong, and then you've got all these imposters in the way. So during my time at ESA, I worked on a paper to help detect these asteroids because we would be getting like hundreds of them, like in any observation. So um,
And you get to, and so were you actually then discovering, like as a side effect of this, you must have been just discovering thousands of asteroids.
So obviously Euclid hasn't launched yet,
Yeah.
but from the simulations, yeah,
Yeah.
like so many different sources, not just asteroids, but for example, variable stars and other things that we didn't want in our data
Yeah.
for weak gravitational lensing measurements.
But some other
And we had to
astronomical
progress.
community. Yeah, some other astronomical community really wants that data.
Exactly,
Yeah.
exactly.
Yeah, it's like the you can sort of see this happening with, say, the Nancy Grace Roman telescope and things like that, where they're going, oh, and by the way, we'll find 100,000 planets,
Yeah,
right? That's not our job. That's not what we're trying to do. But we will also find more planets than have ever been seen
yeah,
as a side effect. And you can see these powerful surveys. I mean, it's the same thing. You see people making these discoveries using Gaia, and they make these follow-up observations, and they say, oh, and then we did a follow-up observation and found 5 more in Gaia. And the Gaia people, I'm sure, just like, I guess, so it's not a thing we were planning in our, when we built the telescope, but if you found it in there, that's great. Love it.
yeah. These kind of surveys, they have legacy for like so many years. So storing this data is actually a huge importance as well. And something I should mention is that, like I did say, we're getting 100 gigabytes of data for Euclid every day downloaded. We don't expect like your everyday astronomer to be downloading that 100 gigabyte of data themselves to analyze. So instead, they've got this ESA labs where you can upload your own code and then run it on their servers, because it would be impossible to download the entire archive of Euclid. It's going to be like petabytes of data
Yeah.
over their 6 years.
And so people are going to be able to come in and run their queries on the data and hopefully be able to come up with some. But I can just imagine, again, it's like just some poor IT person trying to figure out how to run a database that's getting 100 gigabytes added a day.
Yeah,
Yeah.
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 And LSST is going to be even larger, or even SKA.
Yeah.
I think it's like petabytes per day.
Petabytes per day. Yeah, that's madness to think about how you can even store those kinds of sizes.
Yeah.
Sort of blows the mind, and then to try to be able to do meaningful queries on that much data. And yet, Planet 9, all the asteroids, all the Kuiper Belt objects, every supernova, and then all the weird things, and that's the part that I love the most, is just like the weird things that astronomers aren't expecting to find. Someone finds one example of one weird thing, goes, I wonder if there's more. Let's check, let's see if it's in there. And what do you know? It's in 1,000 times inside the.
So that's like a really tricky thing, actually. So with all this big data coming in, people are relying more and more on machine learning to process the amount of data, because like traditionally astronomers would go through by eye looking at the data and spotting these weird objects. But when you're getting that much data coming through, you can't use humans to do this manually. You need algorithms to automate them. And we spoke about machine learning earlier and the importance of the training data. Your algorithms are only as good as your training data. But if you've got a weird object, you don't have any training data on that. So how are we going to spot these like weird and wonderful objects? It's a tricky thing.
Oh, okay. So you have a question. You don't have an answer. You just have like a.
Well, people are working on it. There are there are several people who are trying to develop algorithms to try and spot anomalies in the data.
That's interesting. It's almost like negative space. Like you're trying to find, nope, looks normal. Nope, looks normal. Wait a minute, this does not look normal. And then the computer hands it off to a human who can look a little deeper at it.
Yeah. We definitely still need humans like that. Like machines alone won't be able to do this.
How much? I mean, they always say that software is eating the world. how much of a role does this machine learning have to play on the work you're doing as an astronomer? How much do you rely, do you spin up a Google machine learning cluster every time you need to do a new paper, or how often, how much time do you spend with it?
Yeah, currently all my papers are revolving around machine learning, but I think that's partly also because my research fellowship is machine learning funded. So I teach a master's course called Machine Learning in Science at the University of Nottingham, and that's what funds my research. So
I got a question that just came in from William Vandebeek. Says Dr. Maggie Lieu is applying to become an ESA astronaut. If you have any extra time, could you ask how the ESA astronaut application is going, please? That's such a great question. How's the ESA astronaut application going?
So it only opened like 2 weeks ago, and it's open until the end of May. And I'm in the process of applying, obviously. It's going well. I had my eyes done and they were great. I got accepted for the Civil Aviation Authority, which is needed to get my pilot medical in the UK. So I've got that booked in as well for the end of the month. And if that passes, then I've just got a couple of things to upload for the astronaut selection.
So what were the requirements? Like what hurdles did you have to be able to have on your resume to be able to get into this?
So you have to have a master's degree, I think, there's a variety of subjects. It's not very specific. So science, medicine, engineering.
Right.
It's just quite general. Just be fit and healthy. But actually, ESA are, for the first time, going to be sending a para-astronaut to space. So if someone has, for example, one leg shorter than the other, or some other disability, there's going to be one person selected specifically for that.
Oh, that's
like
great.
They want to test to see if like anyone could go to space, really. They don't want to kind of restrict it.
Yeah.
I think like nowadays, astronaut selections are becoming less and less restrictive, which is good.
Yeah. So you need a master's degree, which obviously you have. You have the next level above that. What else did you, and healthy? I'm assuming you're young, healthy. I'm sure you'll make it. What else do you need? So did you need a pilot's license? Is that why you were?
You don't need a pilot's license, but you need a pilot medical.
I don't understand what that is.
Like a medical test to be a pilot.
The kind of medical test that a pilot would get.
Yeah.
I got it. Okay. All right.
But that specific medical.
Yeah. Good. And when will you find out whether or not you made it?
A month after the closing date, so end of June, I guess.
And do you know how long it might take if you did get it? How long it might take to fly?
So typical astronauts in ESA, they fly after maybe 5 or 6 years of training.
Yeah.
But this time around, like in the UK, it's not like the US. We only have astronaut selections every 10 years. So the last one here was 12 years ago. Wow. So that's a long time ago. Those astronauts, they spent most of their time training before they could fly up. Now they want to have more regular astronaut selections occurring every 2 or 3 years. And so I would expect them to spend much less time training before they could go up because of this overlap of astronauts now.
Yeah. I was going to say, with Canada, we have sort of a special relationship with NASA, and we were able to secure quite a lot of seats through NASA, and so we have a lot. I think I'm trying to remember how many astronauts we've had at this point, like 8 or 9, 10.
Yeah.
And so, I know the round
can apply to ESA as well because Canada is a member, like associative member state.
Yeah,
ESA.
we got options. Yeah.
So Canadians should apply too.
Yeah. Well, but the next round, not this one. You don't want
this round.
Yeah, you don't want more competition this time around. Right.
Well, there's like a lot of, surprisingly, there's a lot of positions this time. So previously, I think they selected 6 astronauts in the previous round. It's usually just a handful. But this time they want up to 6 astronauts and then an additional 20, I think, astronauts that would fly just one time.
Right, right. And so one of the reasons why I reach out to you, in addition to I wanted to talk to somebody from the Euclid mission, but also you're a YouTuber. You're sort of like,
I am a YouTuber.
yeah, you're in the same, whatever that is,
Yeah.
What on earth possessed you to put yourself into the meat grinder of YouTube and actually share your knowledge and experience?
I have been doing public engagement since I was like 18, so since I started university, and my university always pushed me to do like outreach and public engagement. And so I don't know, over the years, I've just developed so much like interest in doing like media. Like I do a lot of TV interviews, I do like things for the university, videos for the university, and it just made sense at some point to make videos for YouTube and just publicize myself a little bit.
Well, but it is interesting. I mean, my experience in talking to other astronomy related YouTubers is the opposite experience that you get, that they get, that the astronomy community in general has a very negative view to people who do public outreach, which is weird because their funding depends on it, and they have a certain portion that they have to put into literally every paper that they do for outreach and so on. But it's like they're trying to figure out ways to not have to be able to actually do that work, and they look down. So have you experienced any backlash to your career from you being such an enthusiastic communicator of science?
I would say that I haven't, but I've heard of stories of people that have, and I've heard like some people say to me that maybe I shouldn't focus so much on YouTube because you should be like publishing papers more and more.
Yeah.
But generally, everyone's been really supportive about doing it, and a lot of like young astronomers, particularly, they always ask for advice, like, how do I give talks at schools, and how do I get involved in outreach? How did you get involved in outreach? And I think that's really nice. I think there's a lot of fellowships nowadays that rely heavily on outreach. And I think one of the reasons that I got my fellowship at the European Space Agency was because I had all this outreach experience. So I think doing it is important, but it's also important to find time to do research as well. You can't just go off and do public engagement all the time. You have to find the balance between the two.
Yeah, I mean the industry, I mean the scientific world, this idea of publish or perish, right? That you have to be writing papers, and if you don't write papers, then you will fall into obscurity. And literally anything that you do, like if you're eating and not writing, you're a bad person. Until you get tenure.
If you have weekends.
If you have weekends and you're not writing, then you're a bad person. Yeah. And that you are, and it, and it comes from such a highly competitive field. And yet, there's so much need for the public to understand the work that scientists are doing, that the taxpayers, they're your bosses, and
they are,
and they want to understand where their money's going.
But there's another thing as well. Like I enjoy doing public engagement because it helps me better understand. Like you can't understand what you're talking about unless you can explain it to a 5-year-old. Like,
yeah, and the same for me. Like when I went to once I started doing this work live, where you sort of just take all comers, every question, no problem, let's do it. It sharpens your brain in ways that allow you to then apply that back to everything else that you do. But it's not, and for me, it doesn't matter. I'm a journalist. I'm just a parasite on the side of the science community, and I don't have any obligations to anybody. But for you, the pressure is you always have to be balancing. Is this paper going to get out the door? I don't have tenure yet. You don't have tenure yet, right?
No.
Okay. So you've got to balance this between publishing and doing this thing that you enjoy. And it seems to be that after a while, these paths diverge.
Yeah, I think so. Well, there's several great scientists that I know of that don't have tenure yet, and they blame it on the amount of public engagement that they do. And it's so surprising. But I think in the US, that's more of a thing, whereas in the UK, we are heavily invested in public engagement.
Yeah, I definitely, and even like Nottingham, like, isn't that where like the 60 signals, is that coming from you guys? Yeah.
Yeah,
So 60 signals, and there's a ton of science channels around that. And so, that is some of the most beloved science YouTube out there, and so that's got to feel good to the administrators, to the people in charge of the departments. And yet the drumbeat, publish or perish, is still probably resonating within the halls of you folks as well. It's a tricky thing. I'm it's interesting to see what I guess I consider where you're coming from to be a more evolved version of research in general, of science in general, that your crew is starting to sort out a better, healthier balance than other fields of academia.
Yeah. And I think like also with like big kind of all these big surveys that are coming online, we're seeing more and more large collaborations. So the Euclid collaboration has over 1,000 members, and like other like big surveys, LSST, have large consortium members, and there is a larger push to do outreach as a collaboration. But then you publish collaboratively as well. So you have more people getting involved in a particular paper, and you have more young people going out and talking about the amazing research that they've done, which really helps, I think.
Yeah.
Like being a part of a big collaboration to support you whilst you're doing this really important work, this important public engagement work.
Yeah, and I sort of imagine in the future perfect world, your ability to explain the work that you're doing to the wider audience, the increased people coming to the university and getting enthusiastic and excited, the recognition by the people who are funding this kind of stuff that this work is important, seeing how an increasingly science literate society is appreciating the work that's being done, that feels like a virtuous circle. And yet it's just like, it's not there yet. And it's, every time I look at it, I just get baffled. I don't understand why. And it's just the incentives are all messed up right now, I think.
I think it's getting there. Well, at least in the UK, I know like at Nottingham, every time I do like a big interview, they always send me the statistics saying, oh, you generated this much ad revenue for the university from this one interview you did. So yeah. I think they're excited about it as well.
But also by our calculations, you could have written 1,000 words during that time of your latest paper.
Yes.
Right. That you didn't do. So, yeah. I mean, I think that on the, like, there's a lot of engagement and a lot of people trying to get people enthusiastic about science, this whole idea of STEM, of science, technology, engineering, mathematics. But it's hard to get a job as an astronomer. There are 100 people applying for a single job. It's almost as hard as trying to be an astronaut. An astronaut astronomer, that's madness. Anyone who wants to do that. So what advice do you have for people who want to maybe follow in your footsteps?
I think you're definitely right that these kind of positions are really hard to come by. And when my PhD supervisor told me about it, he was on the verge of retiring. He retired during my PhD, actually. And he said, I've had over 70 PhD students, and that's how many need to come by to replace me because I haven't retired yet. So there is a lot of competition for tenure positions.
So aren't we setting, I mean, isn't academia, isn't by us engaging with the public and getting them excited about the sciences and encouraging them to go into science also kind of leading them into pain and suffering?
Not necessarily. Like I told you already that I don't stare at telescopes in my day-to-day job. That's not what I do. I spend all my day coding and debugging codes and writing algorithms. So there are a lot of skills that we obtain along the way, and you'll see that most academics, they don't end up in academia. They'll end up in industry, but they have all the skills for big data, tech startups, like finance. We have very transferable skills, problem solving, everything. Like people who learn STEM subjects are kind of brought up in a way that gets them very prepared for the world and do well in the future.
But there's no shortage of jobs in the computer science world or in industry for, machine learning and all that kind of stuff. But there's definitely shortages. But it's easier. Like, why learn magnetoplasmo hydrodynamics when you could just learn, Fortran, right? Like, or whatever, C++.
Yeah, so I had a colleague at ESA. I had a research fellow at ESA, and he worked on magnetohydrodynamics of Jupiter. And now he works for an electric car company modeling the flows around, like, as the autonomous car drives.
Yeah.
How to make it more streamlined. So I think there's still a lot of transferable things. And it's always cool to say, like, oh yeah, I have a PhD in astronomy,
yeah,
and then you end up working for a tech company. That's fine.
Yeah. I don't know. It feels to me like, and again, like I'm part of the problem is that, I'm encouraging people, like there's a lot of people there that are really interested in space and astronomy, and they think it'd be cool to be an astronomer or to be a paleontologist or whatever. And I don't think we want to dissuade them from that career path. But at the same time, they're looking at tens of thousands, if not in some cases hundreds of thousands of dollars of debt. They're looking at a very, very stressful career market that places a ton of incentives on you working very long hours and working very hard and ending up not getting the job that you wanted unless you happen to be at the right time when that one guy retires and the other 69 people didn't get that shot. And how do we both... So, I mean, my feeling is that the answer is citizen science. My feeling is that we channel that love in ways that you don't have to have, that you can be part of the science without having to commit the tens of thousands of dollars and all of that time.
Yeah, and citizen science has been great at doing that. But I think it's also nice to persuade people to do things like this because it's just so much easier to persuade a young kid to study astronomy than it is to study maths or computer science. No offense, but like it's like study the night sky compared to like numbers.
Yeah. Beep boop. Yeah.
Yeah.
I don't know. It's a thing that's kind of tricky, and I just I see it happening more and more, and I tend to ask, when I talk to just straight up astronomers, especially the ones who don't do any out, they're always sort of shocked and surprised when I, like, hey, can I do an interview? And like, who, me, what? Sure. As opposed to somebody who has put themselves out there and is actually out there and engaging. But what have been the benefits for you? Do you find you've been able to bring those skills of the outreach back to your work?
Yeah, absolutely. I think we still communicate science at conferences to other scientists. Like it's surprising, but our field is like so niche. So even if I go to a conference with like 1,000 people, only maybe 5 people will actually know what it is I'm actually talking about in my research. So even going to present my work at conferences like that, I need to be able to have the skills of that I've gained doing outreach to be able to explain to an audience that probably haven't touched your like topic for like tens or even longer years. So yeah, communication skills are really important, and it helps to be like confident about what you're talking about as well.
Yeah, absolutely. I'd love to go through archive and just like workshop people's titles to try and, because like they talk about something really fascinating, but the title itself is really boring. And it's human beings who are scanning through 70 papers trying to pick what's interesting to them. But, someone to zazz those up a bit. And I think, doing some outreach, you see what seems to resonate with people as they go. Euclid's going to be amazing. It's going to do a wonderful job. But if you had access to billions and billions of dollars to answer some fundamental questions that you have about the universe, what super instrument would you love to see deployed?
I would love to have a telescope on like the moon, like a giant telescope. LSST, like Rubin Observatory size, a huge telescope on the moon where we don't have all these effects of like seeing an atmosphere to look through to do astronomy. But it's stable, and I would love to go observing that.
Right. So that's why you want to be an astronaut. I see now. Now I understand. It's all coming together.
I'll go and set up my telescope on the moon.
Yeah, you're just going to go out there with your whatever 14 Celestron, set it up on the out on the regolith, and then like looking through the eyepiece through your yeah, no, I understand that. The moon, I don't know, the moon is moon's hard to get to. Not just a space telescope. I mean, couldn't you do it better in space? I mean, it's something I mean,
well, at least it's like stable. There's no like, I don't know. I think it's a good place to go.
Yeah. Well, I think exactly, and I think that really supports the case that you're really the only person who can go there. You're a unique asset to the team, and you really need to go to the moon. It's kind of scary to think. I mean, if you do get on as an astronaut, then yeah, you could be walking on the moon.
Yeah, that would be really cool.
Yeah, please tell me how that goes. Because
we'll have to do another one of these Q&As. What's it like on the moon?
Yeah, with a 2-second delay. So, Maggie, where can people find out more about you, what you're working on, and what's the best place?
So I have a website, maggielieu.com. You've already linked it in the description box. I have a YouTube, space_mog. Yep. I'm on Twitter, active on Twitter all the time. You'll find me on the archive. I publish papers occasionally, probably less than I ought to.
Don't perish. You haven't got tenure yet. Hurry. You should be writing.
It's good to have students. I've found I've got a lot of students, and they tend to do all my writing for me. It's wonderful.
I don't think you were supposed to say this live, but awesome. And what specifically what cool things should we see next that you're working on, apart from a completed and successful astronaut application?
I've got this new paper coming out soon. And it's emulating the winds of black holes. So it's a machine learning network to kind of model black hole winds, which for some reason, the astronomers that work on these kind of things use simulations that take months and months to run. Machine learning does it in seconds. Fraction of a second. So
right. Fix that for you. Yeah, save you some time. Well, Dr. Maggie Lieu, it's an absolute pleasure to talk with you, and congratulations in advance for becoming, the next Europe's next astronaut, and all the work you're doing with Euclid and the Dr. Maggie Lieu Observatory on the moon. I look forward to all of it. All right. Thank you so much, and thanks for taking the time to talk with us today. And now have to find the buttons. Where'd it go? Wait a minute. Wait, I lost it. I totally lost the button. I can't stop this. Oh, wait, here we go. All right, I did it.